So much of the real world comes down to one question. What is the biggest or the smallest value some quantity can take? The most area for your fence, the least metal for a can, the shortest possible route. Every one of those is a hunt for a maximum or a minimum. Picture walking along a hilly road like this one. There are several little hilltops and several dips. Every hilltop is a local maximum, the highest point in its own little neighborhood. Every dip is a local minimum. There can be many of each, but only one point is the very highest of them all, the global or absolute maximum. And only one is the very lowest, the global minimum. Those two are usually what we actually want. Before we optimize anything, a quick refresher on how we tell a peak from a valley. It all starts at the flat spots, the critical points where the slope is zero. The second derivative sorts them out in a heartbeat. If f double prime is negative, the curve bends downward like a dome. A flat spot on a dome is a maximum. If f double prime is positive, the curve bends upward like a ball. And a flat spot at the bottom of a ball is a minimum. Dome, maximum. Ball, minimum. That is the whole test. Let's put it to work on a real cubic. F of x is x cubed minus 3x squared plus 2. Differentiate. 3x squared minus 6x, which factors as 3x times x minus 2. Setting that to 0, the critical points are x equals 0 and x equals 2. Differentiate once more for f double prime, 6x minus 6. At x equals 0, f double prime is minus 6. Negative, so a local maximum, and its height is f of 0 equals 2. At x equals 2, f double prime is plus 6. Positive, a local minimum, sitting at minus 2. Two flat spots, cleanly classified. Now, the single most useful procedure in this whole topic. Suppose your function is continuous on a closed interval from a to b, and you want the absolute biggest and smallest values on it. There is a foolproof three-step recipe. The reason it works is beautiful. An absolute extreme can only hide in two kinds of place: a flat critical point in the middle, or right at an end of the interval. Nowhere else. So you just evaluate f at every candidate and compare. Watch it on a real function. Take f of x equals x cubed minus 3x on the closed interval 0 to 3. Here is its graph over that stretch. Step 1. The critical points. F prime is 3x squared minus 3, which is 0. When x squared is 1, that's x equals plus 1 or minus 1. But minus 1 is outside our interval, so we throw it away. Only x equals 1 counts. Step 2. Gather every candidate. The critical point x equals 1 plus the two endpoints 0 and 3. 3 points to check. Watch them light up on the curve. Step 3. The value table. Evaluate f at each. At x equals 0, f is 0. At x equals 1, our critical point, f is 1 minus 3, minus 2. And at the endpoint x equals 3, f is 27 minus 9, 18. Now just read off the winners. The largest value is 18, the global maximum, and it happens at an endpoint, x equals 3, not at any critical point. The smallest is minus 2, the global minimum, at x equals 1. And that is the lesson's biggest warning in one picture. Time for the real payoff. A word problem. A farmer has 100 meters of fencing and wants to pen off a rectangle against a long straight wall. The wall is free, so fencing goes on only 3 sides. What shape gives the most area? Let's give the two equal sides a length, x. Then the side running along the wall must use up whatever fence is left, 100 minus 2x. Watch the pen change shape as I slide x. And keep an eye on the area. Too slim and there's no room. Too deep, and the width collapses. Somewhere in between the area peaks. Let's find that sweet spot exactly. The objective is the area. A of x equals x times 100 minus 2x, which expands to 100x minus 2x squared. Differentiate. A prime is 100 minus 4x. Set it to 0 and x equals 25. Is it really a maximum? A double prime is minus 4. Negative everywhere. A dome. So yes, a genuine maximum. Now finish the job. The width along the wall is 100 minus 50, which is 50 meters. And the area is 25 times 50, 1250 square meters. One more, a little richer. A cylindrical can must hold a fixed volume, say a standard 355 milliliters. A manufacturer wants to use the least possible metal. What radius and height do that? Set up the geometry. The volume is pi r squared h, and it's fixed at 355. The metal is the surface area, two circular ends, 2 pi r squared, plus the wall wrapped around, 2 pi r h. But area depends on two variables, r and h. We can only differentiate one, so use the constraint. From the volume, h is 355 over pi r squared. Substitute that in, and the 2 pi r h term becomes 2 times the volume over r. Now everything is in r alone. Differentiate with respect to r. The derivative of 2 pi r squared is 4 pi r, and the derivative of 2v over r is minus 2v over r squared. Set it to 0. Rearranging, r cubed equals the volume over 2 pi. Take the cube root. The best radius is about 3.84 centimeters. Feed that back through the constraint, and the height comes out about 7.67 centimeters. There's the elegant punchline. 7.67 is exactly twice 3.84. The most metal-efficient can is as tall as it is wide. Its height equal to its diameter. And a double prime comes out positive, confirming it really is a minimum. Nature loves that little square profile. Let's crystallize the whole method into one checklist you can run every single time. First, name the variable. Give the unknown a letter, x. Second, write the objective, the quantity you want, biggest or smallest, as an honest formula. Third, and this is the crucial one, apply the constraint to squeeze everything down to that one variable before you touch a derivative. Fourth, differentiate. Fifth, solve f prime equals 0. Those are your candidate points. Not yet the answer. And sixth, classify with the second derivative test, then state the answer properly with units. 6 steps and every optimization problem falls. Your turn, and this is a classic. Two positive numbers add up to 10, which to make their product as large as possible. Pause the video, run the recipe, and find them before I do. I'll wait right here. Here's the walkthrough. The constraint x plus y equals 10 gives y as 10 minus x. So the product p of x is x times 10 minus x. That's our objective in one variable. Differentiate. P prime is 10 minus 2x, 0 when x equals 5. And p double prime is minus 2, negative. So it's a maximum. Both numbers are 5, and the biggest product is 25. If you landed there, you've truly got this. Trap 1. And it's the deadliest. Forgetting the endpoints. On a closed interval, the global maximum or minimum can leave right at an end. Remember, our fence graph peaked at x equals 3, an endpoint, not a critical point. Always evaluate A and B too. Trap 2. F prime equals 0 only hands you candidates. A flat spot could be a minimum when you wanted a maximum. Always confirm with the second derivative test before you celebrate. Trap 3. Trying to differentiate with two variables still in play. Use the constraint to get down to a single variable first. That's the whole trick that makes it solvable. And trap 4. Check your answer is physically possible. A length, a radius, a time can't be negative. So quietly discard any route that falls outside the sensible range. Let's lock it all in. Maxima and minima always begin at the flat spots, where f prime is 0, your candidates. Classify them by curvature. F double prime negative is a dome, a maximum. Positive is a ball, a minimum. On a closed interval, check the critical points and both endpoints. Then compare the values. The largest wins, the smallest wins. And for any word problem, run the recipe. Name the variable, write the objective, use the constraint to reach one variable, then differentiate and solve. Master that, and optimization becomes something you simply do.